the last topic we're going to cover in this chapter is phase diagrams. And so these are a very important tool for mapping out basically what phase something is in. So, is it a solid or a liquid or a gas? So we're going to talk about what supercritical fluid is in a little bit. And essentially it just plots pressure versus temperature. So if we have like a gas and we compress it, we can get it turned into a solid or a liquid, depending on what temperature we are. Or we can take a solid, we can heat it up and we can get a liquid. And if you're in the right spot, you can heat it up more and get a gas, or you can get a supercritical fluid, depending on where you are, what pressure you're at. So, what we are seeing here is what area our phases are. So over here we're a solid, over here we're a liquid, over here we're a gas. But these lines also denote phase changes. And so if we're going from solid to liquid, oh, well, that's melting, right? Or freezing if we go the other way. If we go from a solid to a gas, that's deposition, or, if we go the other way, it's, sublimation. So sublimation / deposition. And gas to liquid, well, this is evaporation or condensation. And so there's a couple key features on here. First one is we've got this triple point. And when we have a triple point, whenever we're on one of these lines, if we're here, right on that line, that means that there's some solid and some gas present. If we're over here, it means there's some some solid or some liquid present, some mixture. We're transitioning from one to the other. It's moving, but things have to melt or, deposit or whatever, depending what phase transition we're doing, or evaporate. But if we're on this point right here, all three phases are present. That's what we call a triple point. 1, 2, 3, triple point. All three phases are present in our container at that temperature and that pressure exactly right there. You'll see some solid, some liquid, and some gas. All three of them will be present. You'll be transitioning from all over the place, from one state to another. And depending on which way we push it, we can into all liquid, all solid, or all gas, just depending on what we do here. Whether we cool it down, pressurize it, decompress it, heat it up, whatever we do. Okay, and then we have the critical point here, and this is where supercritical fluids start showing up. This is actually not always a hard line. It's usually kind of a fuzzy area over here. Like there's some spaces where it's definitely supercritical and some spaces where maybe it's a little more gas or liquid-like. It can shift. And so you probably haven't heard of supercritical fluids before. They're a very key idea. Very interesting to study physically. But essentially it's this area where we have kind of gas and liquid properties occurring with our substance at the same time. So for example, liquids dissolve things. Gases don't tend to dissolve things. So it will dissolve things like a liquid does. But it also doesn't just sit at the bottom of the container. You don't fill it up. It will fill the entire space of the container like a gas. So it behaves like a liquid and a gas at the same time. And it's really got some cool properties. One of the more interesting ones to me is that there's zero viscosity. So if you have like a beaker and you were to pour a supercritical fluid into it, it would go down one side of the beaker and it would shoot right back out the other side. That's what it would do. There would be no drag on the container slowing it down. So it would just shoot through. No friction. Just pours itself right back out. So I imagine they're a little tricky to deal with. Generally they're in closed containers though, because they're going to behave like a gas. So they're just going to go everywhere. But that's what a supercritical fluid is. And so when we kind of back up here to the phase diagram, now that we've kind of explained all the pieces, generally you're going to see low pressure, high temperature, gas phase. High pressure, low temperature, solid. Liquid is kind of in the middle, and then supercritical fluid's always out past liquid and gas. And so you can get different shapes of these lines for different substances. So this is just a general example. And so this would be something that turns into a solid as you pressurize it. So this would be an example of maybe what waters would look like. But oftentimes this line can bend back as you compress things, or if you pressurize it, turns into a solid. So that's pretty normal. Actually, water bends back. That's what it is. Water's weird. So the water line bends back and you can compress the solid into a liquid because ice expands. That's not very normal. It drives all of like our geological processes, soil formation, erosion, all these ideas, you know. That's why we have to do, you know, there's 2 seasons in the Midwest, right? There's winter, and then there's road repair season, because they have to repair all the ice damage in the road, because the water gets in, it freezes, it expands, and it breaks the asphalt apart, it breaks concrete apart, eats that stuff up. And so water is unusual, and that line bends back. So these can move around wherever, but generally you're gonna see gas, solid, liquid, supercritical fluid. But the positioning overall will be the same, but the lines can be different. So be aware of that. And so one way to kind of anchor your mind in this is, well, if you make something cold and pressurized, you got to have solid up here. You got to have gas down here, and in the middle is liquid. Because if you're going to have it hot and low pressure, it's got to be a gas. If you're going to have it cold and really pressurized, that's going to be a solid. And so you don't have to worry too much about the shape of the lines. But you know, we can also do stuff like, let me get another color marker here. You know, if we start at this point, we'll call it, I don't know, point A, right? And then we transition to maybe point B. You know, what happens? Well, condensation happens right here. We go through this line, we condense into a liquid, and we stay a liquid. So we start a gas, we condense, we become a liquid, stuff like that. And then maybe we cool it down, and we get to point C, in which case we freeze it, we solidify it, now we have a solid. That's what we're doing. And then we can bring it back to point A. What would we do to point A, to get to point A? Well, we'd have to heat it back up, and then we'd have to drop the pressure. That's what we would do. Okay, so that's kind of how you read these phase diagrams and some general trends for what you're looking at them. What the triple point is, what is a supercritical fluid? Because you probably haven't heard of it before now. One key use for supercritical fluids is kind of, what should I say, more environmentally friendly dry cleaners will use supercritical CO2. If you compress it, you take dry ice and you put it in a pressurized container, it will turn into supercritical CO2. Don't do that, because the container has to be built for the pressure. If not, it explodes. If anyone's ever seen, you can look up what happens when you put it in, like, say, a soda bottle on YouTube. Don't do this. It's called a dry ice bomb, because essentially the plastic will give way, and then there's a sudden change in pressure, and that's an explosion. But they can use supercritical CO2, and they can clean clothes, so they don't have you know, less environmentally friendly solvents they have to deal with down the road. The CO2 just turns into gas and it goes away. And you can just get it back from the atmosphere through capturing processes. So there's all sorts of stuff about CO2 in the atmosphere. Using supercritical CO2 in a dry cleaner is net neutral as long as you're taking the CO2 from the atmosphere and putting it back. That's fine. If you're, you know, adding extra CO2 to the atmosphere, that's when there's an issue with that stuff. So that's why it's a little bit more environmentally friendly to do that. But anyway, that's what these phase diagrams are. So they just show us where different phases are at different temperatures and pressures. And you might have specifically labeled points. You know, we can have our temperature here and a pressure here for our triple point, temperature and pressure for our critical point, so on and so forth. I kept mine very vague and general. So just be aware that there might be numbers you have to read off these axes as well. And that's kind of last detail. So that's it for chapter 10. So we're going to move on to chapter 11. So we're going to move away from pure compounds and how they're interacting. So large groups of the same molecule interacting with each other, with the exception of the solubility section. That's what we had in this chapter. We just had, you know, I have a bunch of water molecules, or I have a bunch of, you know, octane molecules. I don't know why those are all in my mind today. Once they get locked in, it's over. Or CO2 molecules. Now in the next chapter, we're going to talk about, well, what if it's a mixture? And we're going to talk about a lot of these same properties, but mixing substances together will change their behavior. So we have to be aware of that. And we will talk about how we can measure those differences. There would normally be a lab that you would do in person, where you would measure a difference in freezing point as you add a solute and generate a solution. And you can figure out the molar mass of it and things like that. So there's going to be definitely more math in chapter 11. So sharpen up those calculators and get ready.